Oh, there is a problem in my mic, but everything is okay. Okay, cool. Okay, let's start then. Is my screen visible? Can anyone confirm? Yes, okay. Let me see if recording. Yeah, it has started. Okay, so everyone, welcome to the fifth week of this interactive sessions for classical mechanics. So far we had been looking at some problems involving Lagrangian coordinate transformations, etc., etc. Right. So, and then we looked at normal modes and frequencies for those modes, etc. So this week I'll start with a brief recap as our tradition is. And so this week we started with 1D systems, right? For which Lagrangian would look like half q dot square minus u of q. So we have absorbed the mass or any other coefficients into the time, assuming they are constant. Then the Hamiltonian of this system would simply be half q dot square plus u of q, right? And then we can solve this system uh, by considering that this is a constant number e. This is constant, okay? Which means I can write q dot as uh, what would it be? Square root of, yeah, 2 times e minus u of q, from which we immediately see that the potential should be less than the total energy of the system, right? So we can integrate this. So we have this dq by dt is equal to square root of 2e minus u of q. So integral of dt, let's say from 0 to t, okay, maybe I should write dt time, would be integral dq by square root of 2e minus u of q. Again I can use prime here, and this is from q0 to q of t, right? So just to mention, we should keep track of degrees of freedom and number of constants that we can have. So since from Lagrangian we have a second order differential equation, we should have two constants of motion. So the first one comes from this energy, whatever total energy is, and the second one is from initial condition. I mean, the energy is also fixed by initial conditions, but there we have two constants. Okay, so this is the formal solution. In principle, you can solve any 1D problem now using this equation. Okay, then the next thing, yeah, we learned one thing, which is that time period of oscillation, time period t is independent of amplitude if and only if u is proportional to q square, that is u is quadratic in q. Okay, and then we started with two body problem. For two body problem, right? So we have one mass here and one M2 at some R1 and R2. Okay, and the assumption was the force is central, which means the potential, which could be in principle function of both these vectors, is actually a function of R1 minus R2. Not just that, it's a function of just the distance, the scalar distance between the vectors. And this came from the argument that space is homogeneous and isotropic, right? So under this assumption, we are able to reduce the system which initially had 6 degrees of freedom, right? 6 R1 and R2. From that, we got first that center of mass, velocity of center of mass should be a constant, some constant vector k. And so we had just 3 degrees of freedom, which was small r, right? Which is R1 minus R2. And then we considered two things. Angular momentum is constant, right? So, and there is an axis along which there is no motion. So since angular momentum is constant, you have a plane of motion. So perpendicular to that, we are calling that axis to be z. That is constant or 0. We can define our coordinates such that z is equal to 0. So then we are reduced to only 1 degree of freedom. Okay, which is just r, the distance between two of them. We know that if we know the potential, then for 1D we have already seen that we can solve the system. So for 1D, what we get is finally the effective Lagrangian is half, or let me write Hamiltonian, mu r square plus, let me see, half mu r square theta dot square and minus u of r, right? And we can write this as half mu r square plus some u effective of r, which is just your energy. And this is the sum of these two. So half, we can write L square by mu r square, right? Because your L is mu r square theta dot. Okay. L is mu r square theta dot, which is constant, and minus u of r. So this is an effective potential if you are looking just at the radial distance from the origin and nothing else. Okay. So now you can put this u in the equation that we derived earlier, this one, and you can solve for r as a function of t. And once you know, once r of t is known from above, we can immediately calculate theta dot, which is L by mu r square, from which theta of t is also known. And then we know everything about the dynamics of the system. So this is the approach for two-body system. And there was one remark, which was second law of Kepler. It says that areal velocity, which is the rate of area that is swept by a particle about the origin, is constant, and not that it's independent of nature of interaction, right? It need not be under gravitation. The planet could have force other than 1 by r square as well. As long as it is central, this law holds good. so independent of interaction. Okay, and then we saw some examples for potentials, right? Example, U of r could be half k r square, that is your spring, then minus k by r, this is gravity. In general, it could be minus k by r to the power n, some attracting force, or it could be minus k over r, gravity, with some damping term, r by r naught. This is Yukawa-like potential. This is gravity, and this is spring or Hookean interaction. Okay, and we saw one thing, that for circular orbit, we have r0 to be L square by kb, where mu is your effective mass, m1 m2 by m1 plus m2. Okay, so after that we kind of switched the gears and went into maths, coordinate geometry, and conic sections, right? Conic sections in polar coordinates. So the way professor derived everything was, first look at them in your normal Cartesian coordinates, then use x is equal to r cosine theta and y is equal to r sine theta. Substitute them, and at the end you get r as a function of theta. That is your polar equation. And what we found at the end was an amazing thing, that r is equal to alpha divided by 1 plus epsilon cos theta describes all conic sections. So the reason they are called conic sections was is that if you have a cone of some angle, half angle theta, yeah, and if you cut them, take a intersection with a plane, then at the boundary you get all these sections, right? So first of all, if the plane is horizontal, that is perpendicular to the axis of the cone, then the section that you get is circle. So this has a eccentricity 0 and it's circle. Okay, so the equation would be r is equal to alpha, right? Epsilon is 0. We can cut it slightly at an angle, but not too much, and what you get is this kind of elongated circle. So epsilon greater than 0, but it's less than 1, and now it's ellipse, for which you have r is equal to alpha divided by 1 plus some number epsilon between 0 to 1 cosine theta. Okay, then what you can do is cut it at an angle which is just parallel to this slant line. So it would be something like this. And if you cut it, the intersection would look like this. Maybe I can use different color. Yeah. So this is parabola. Okay. When epsilon is just equal to 1. And if you have even higher angle, then what you get, let me use other color, orange, is hyperbola. So that's why they are called conic sections. Okay, if you imagine there is another cone downstairs, let's say something like this. Then eventually this plane would cross here, and you will have another branch of hyperbola. So hyperbola always comes in pairs. Okay. And by the way, this is something that you can do at your home also. If there is a birthday party of anyone, we use this kind of caps, right? So after the party, if you or you can tell your younger siblings to do this. If you cut these sections at some angles, you will see circles, ellipse, parabola, everything. It's a fun thing. Okay, so this was kind of a brief recap, and we can do that in Mathematica also. I'm sure some of you have already tried. I also did. So this is a simple two-line code that I wrote. So I defined conic of three, which is a function of three variables, a, e, and t. A is your amplitude or alpha in the equation. E is the eccentricity or epsilon, and t is your basic angle theta, right? Which is, and the equation is a over 1 plus epsilon times cos theta. Then I'm using this function called manipulate. So it gives us handle to select the parameters which we want to manipulate or change. So the polar, oops, polar plot of conic of a, epsilon, and t, and the angle t or theta goes from 0 to 2 pi. And then I'm telling the program to have a between 0 and 10 and e between 0 and 2. So that gives me two handles for a and e. So let's keep a to be something. Okay. And e, let's start from 0. So for 0 we have circle. For 0 we have circle. As I increase epsilon or eccentricity, it becomes slightly elongated in one axis, and you get ellipse, right? More the eccentricity, more the elongated ellipses, or more eccentric the ellipses. At 1 it becomes parabola. As I increase epsilon, now we have hyperbola, right? And then the hyperbola just gets modified and wider. Okay. And a basically determines the amplitude or the size of the ellipse. It is, to be precise, it's b square by a, where b is semi-major axis and a is semi-minor axis. Okay. So any questions so far? Can you please explain the bead problem, how generalized coordinate was selected there after this recap? Okay, let's solve some questions first, and after that we can come back to this. I'm not sure exactly which problem are you referring to, but we'll discuss that later. Thanks. Okay, so uh, last semester I found three problems, all of them very easy. I'm sure most of you can do it on your own, but let's just see how they are done. Okay, so the first one is, we have one dimensional system around its equilibrium position, and the potential is u is equal to alpha times q to the power 4, where alpha is greater than 0 and t is the time period when the system has total energy E. Then upon increasing the energy to 2E, time period will, what will happen? We know for a fact that if had this been q square, then the time period does not change. But now it's biquadratic, q to the power 4. So the potential landscape would look something like this. Okay. Visually, it looks just like a parabola, but it's increasing faster than a parabola. This is q axis and this is u of q, right? So and the energy is given to be some E, and what would this point be? This is some q0, then we know. So without loss of generality, we can just assume alpha to be 1 so that our calculations are more easier. Anyways, the answer doesn't depend on alpha. So, and alpha has to be positive that we have taken. So this is again a side remark when you have such questions in, especially in exams like GATE or NET, you can simplify by using some parameter value, which the answer does not care about, right? So then u of q is simply q to the power 4. Okay, and now we need to find q0. So we know u of q0 should be the given energy of the system, which means q0 to the power 4 is E. So q0, the positive one, is e to the power 1 by 4. Cool. Now that formula for time period was derived in the class. It's 4 times integral of, let me look at the formula. Yeah, 0 to q0 dq prime divided by square root of 2 e minus u of q prime. Let's substitute for u of q prime. So we have 0 to q0 dq prime divided by square root of 2 times e minus q prime raised to 4, right? And clearly this can depend on energy. We have energy here, and this q0 also has dependence of energy, and we want to take that dependence out of the integral, right? So we can substitute q prime as some q0 times x, let's say. So as q prime grows from 0 to q0, x will go from 0 to 1, right? So then t becomes 4 times 0 to 1. Dq prime would be q0 times dx, and square root of 2 e is q0 raised to 4, right? And this is, oops, this is q0 raised to 4 times x raised to 4. So t becomes, now we can take all the q0s outside. So we have 4 times q0, and from the denominator we have q0 raised to 4, but then there is a square root, so it is q0 square, right? And then the integral dx from square root of 2 1 minus x to the power 4. So it's t is proportional to q0 raised to minus 1, which is, and since q0 itself is proportional to e to the power 1/4, this is proportional to e to the power minus 1/4, right? So t is proportional to e to the power minus 1/4. This is our result, which means if E goes to 2E, that is what is given in the problem, right? So if total energy is doubled, what happens? Then T goes to 2 to the power minus 1/4, this factor, times T. So the answer is 2 raised to minus 1/4 times. So it decreases by a factor of 2 to the power 1/4. Okay. So there is a slight ambiguity in the semantics. Ideally, when you say decrease by some factor, it means it is reduced, it is divided by that factor. So technically it should be just 2 to the power 1/4 because you are already saying it's decreasing, but that's the way it's framed. Anyways, it's not increasing by either of this factor. Okay, so that's that. Is that clear? Okay, I'm assuming so. If something is unclear, you can just ask me at the same time. Okay. Next two questions are kind of qualitative and very easy. And what is given is you have one-dimensional system that is described by UQ, which is shown in this figure. Right. The turning points of E is equal to E1 are at. So for E is equal to E1, what are the permissible points? So we have E1. This is okay, this is E1. So whenever the total energy does not go down the UQ, it's permission, right? So these green lines are the region where the particle is allowed to be classically. Of course, in quantum mechanics, you have tunneling and all. But classically, this is the permitted region, and this would be forbidden region, right? Because here you have potential higher than total energy, which means your kinetic energy is negative. That does not happen. So this is not allowed, and green is allowed. So for E is equal to E1, where are the turning points? It's where these two regions meet, right? So if you start your system from here, it will climb up to this point and then come back. Okay. So the points are Q1, Q2, Q3, and Q4. So that is your answer. For the second one, we have the same thing, same potential, and which of the statements are correct. So the first statement is in the region Q2 less than Q less than Q3, kinetic energy would be negative if system has total energy is equal to E1. Again, for E1, the allowed region, there are two regions, and it's saying in the region Q2 less than Q less than Q3, which is this region, kinetic energy would be negative. And that is correct, right? Because this is not allowed. Total energy is less than the potential, which means kinetic energy is negative. So this is correct. And the second one is if the energy is equal to E2 in the region Q is less than Q0. So now this is E2. So in the region Q less than Q0, it's not allowed, right? And similarly for Q greater than Q5, it's not allowed. Within those 2 points, the system is allowed to exist. So in the region Q less than Q0, system would have imaginary velocity if its energy is equal to E2. Is this correct or not? Anyone?
I think it's not correct.
Okay. And why?
Imaginary velocity, I'm assuming it is something to do with the complex numbers, but velocity has to be real. So it can be negative, but it cannot be imaginary.
I see. Okay. So yeah, that's the thing. In the same way, you can say that kinetic energy can also never be negative, right? Then is the first option incorrect?
No, it's not incorrect, but yeah, yeah, sure.
Sure.
I
So
get that point.
you get that sometimes it's the semantics that gets us. So the definition here is that kinetic energy, what is defined as total energy E minus your potential, whatever that is. So obviously in this region, this value is negative. Does not mean if the particle is there, then it will have a negative kinetic energy. It simply means that particle cannot be there. But if you just mathematically blindly put down the numbers, your kinetic energy would turn out to be negative, which is why this is correct. Now, if the kinetic energy is negative, is some negative, then your V is square root of a negative number, right? Which is imaginary. So if you define your V to be square root of 2 times kinetic energy by mass, then it is imaginary. And in that sense, this is correct. Uh, do you get it?
Yeah,
Yeah?
understood. Yeah,
Cool.
yeah.
Okay. So those were three questions which were there in previous year's assignments. One thing I can do, one more thing is, we solved this for q to the power 4. Maybe we can solve this for a general n. Let's see if we can find something. So the fourth is same as question 1, except u of q is alpha q to the power n. And let's see if we can first of all find for a general n, and then see if we put n is equal to 4, do we get the same result or not. Okay, so now we have again we'll have q0 as, I'm not writing everything, e to the power 1 by n, right? Same as 1/4. And then we can do the integral. Time period is 4 times 0 to q0 dq prime divided by square root of 2 e minus q prime u of q prime. So 4 0 q0 dq prime square root of 2 e minus, this will be q prime raised to n. Okay, again same thing, q prime we write it as q0 into x, so that x goes from 0 to 1, and now the time period becomes 4 times 0 to 1 q0 dx square root of 2 e is now q0 to the power n. I'm rushing it because we have already done that. So q0 raised to n and x raised to n, right? And now we can take out q0, it's 4 q0 from the numerator, and from the denominator we have n by 2, right? Because we have square root also. And then a funny integral which we don't know how to solve. Maybe some of us know, but doesn't matter. It's just a number, right? Same as previous. And then q0 itself was e to the power 1 by n, right? So now you have 1 by n times 1 minus n by 2, so it's 4 to e to the power 1 by n minus 1 by 2. So that's your answer, or 2 minus n upon 2n. Okay, so if you are just looking at dependence, it is this one. This is for generalized n, and then we can look at the case for question 1, for which we had n is equal to 4, right? So we had t is proportional to e raised to 2 minus 4, which is minus 2 upon 8, which is e raised to minus 1 by 4. Okay, so it checks out. Another case which we know is that if t does not depend on e, which means it's proportional to e to the power 0, it means 2 minus n upon 2n is equal to 0, which means 2 minus n is 0, which means n is equal to 2. So we have recovered what we learnt in our class, right? When n is equal to 2, the time period does not depend on the amplitude. And one thing we can see from this fact is that for SHM it's true, because we have energy as half kx square, but for pendulum, right, we have energy or the potential as a function of h, or sorry, as a function of theta, as mgl 1 minus cos theta, right, if you remember. And that that is quadratic, so this will be theta square over 2. Cos theta is 1 minus theta square over 2, so it's proportional to theta square over 2, but there are other higher order terms, right, theta raised to 4, etc., which makes the system non-linear, and then the time period would actually depend on amplitude. So if your theta is higher, then the time period would be function of your amplitude. You can think whether it increases or decreases with amplitude. Okay. Okay, so that's all from my side for this week. If you have any questions, uh, one of you had a question, right? Amarnath, can you please explain the bead problem? How general? So, what exactly do you mean by bead? The bead is on a uniformly rotating wire. Oh, okay. So you are asking from some first session or second one. Okay, so let me see if I have it in my notes. Okay, it's not there. So correct me if I'm wrong. You have a wire, okay, and it's rotating with some angular speed omega, right? Bead problem. And so you just have 1 degree of freedom, which is r, okay, and then we know that Lagrangian of do I have it here? Yeah, so Lagrangian would be half m r dot square plus r square theta dot square. This is for a particle in 2D, but it's in a free space. So correct me if I'm wrong anywhere, because I don't have the notes right now. So r dot square is something plus r square omega square, right? Because theta dot is omega. And now this is a Lagrangian of just one thing, one variable, which is r. Now we can write Euler-Lagrangian equation of motion, which is d by dt of del L over del R, which is d by dt of, with respect to r, it would be m r omega square. Is that correct? Yes. Which is m r dot omega square. And oh wait, it should be r dot, right? So this is m times r dot, which is just mr double dot. And now L by del r, which is derivative with respect to r, is mr omega square. And then you equate these two, so we get mr double dot is equal to mr omega square, or r double dot is equal to omega square r. Okay, so this is your equation of motion. And then you can, since you know the Hull charge e to the power some kt would work, right? So if you have some a times e to the power kt and put it in this equation, then you get a k square e, e to the power kt is equal to omega square a e raised to kt. So this a gets cancelled, exponentials get cancelled. You have k square is equal to omega square, which means k is equal to plus or minus omega. So your solution becomes r of t is some other a, not the same necessarily, e to the power omega t plus a times e to the power minus omega t. Okay, so I believe that was the problem and this was the solution. Now tell me which part did you not understand. Here theta is also changing with time, and why you select only r as generalized code. So we started with two coordinates, right? Here we have L as a function of r and theta, not so r dot and theta dot, right? In which this theta dependence was not there, but theta dot was there. But then we also had oh shit, thank you. So this first expression we had theta dot, right? But when we knew one constraint, which was theta dot is equal to omega. Since the wire is rotating at a uniform velocity, we have solved for theta, which this means basically theta is omega t, right? And so you can either think that we have solved for one generalized coordinate, so now we have only one generalized coordinate from two, or you can think as there is a constraint for the particle, which is that theta has to be omega t, and because of that constraint we have one less generalized coordinate than usual. Does that make sense? We are applying constraints. Exactly. Thank you, Meenakshi. Okay. Okay. Anything else? Anyone? Hi, Raku. Do you have any questions? Anything?
Not yet.
No. Okay. I remember you asked me one question long back. I don't know what that was, but did it get solved or is it still unsolved?
I don't. I also don't remember.
Okay, cool. So if you have any questions during watching the lectures, you can always email me. My email ID, if you don't know, it's I'll type it on the chat box. arshtotalia@iitb.ac.in. You can send Y H and L significance. What? Oh, the Hamiltonian and Lagrangian. So Lagrangian, as we learned, can come from understanding the constraints of the surfaces, etc. And another way to naturally derive Lagrangian would be to consider the action and minimizing that action, the path that minimizes the function called action, naturally gives us the Lagrangian, the expression for Lagrangian. We are going to do the second approach towards the end of the course, so just wait for it. So Lagrangian is a natural quantity to describe your system, but it's not conserved. It's generally kinetic energy minus potential energy, not always, as we saw earlier. But from taking the time derivative of Lagrangian, if you remember, you discovered a quantity that was conserved, and that was the energy of, or the Hamiltonian of the system. So in that way, Hamiltonian is derived from the Lagrangian, but then it's a very convenient quantity because it remains constant. So as we saw from the fact that Hamiltonian remains constant, we calculated for 1D case, right? We did not explicitly mention Euler-Lagrangian equation. So both of them have significance in their own right. H is not conserved for time dependent. Yes, yes, of course. Also, if there are coordinated transformations involve time, then also it's not conserved. We looked at it in depth, right? But even when H is not conserved, we know exactly how H changes with time, because we know dH by dt is minus partial dL by dt. So from the Lagrangian, we know that how it depends explicitly on time, and from that we know how H changes with time. Okay, cool. Anything else? Anyone? Okay, then we'll meet next week, next Tuesday, and that will be the week 6, which means we are at almost the middle of the course. I hope you are keeping up, everyone, those who watch on YouTube also. Okay, so all the best for week 6. Happy learning.